Hello, and thanks for reviewing the following presentation given during the 2020 Data Science Symposium webinar series. The Data Science Symposium is one of several services provided by the University of Cincinnati's Center for Business Analytics, a part of the Lindner College of Business. Through leadership forums, student projects, public education events, including the Data Science Symposium and the Analytics Summit this spring, as well as professional development courses, the Center provides businesses and organizations with game-changing capabilities to drive analytics for competitive advantage, regardless of size or type of organization you represent. For more information about the Center, including how to join our 25 member organizations and the benefits they enjoy, please contact either myself or Dr. Michael Fry here at UC. Now, enjoy the following presentation.
Hello, welcome to the University of Cincinnati Data Science Symposium. My name is Youngsu Chen. My presentation today is titled Leverage Forecasting Power of Classic Time Series Models and Deep Learning. So a little bit backgrounds about myself before diving into our topic today. I'm currently a data scientist at Amazon Web Service. For the past 2.5 years, I've been working at Amazon as a data scientist. And before joining Amazon, I was also working as a data scientist at the national nonprofit organizations and an adjunct at the University of Nevada, Las Vegas. I've been in the data science field since I received my PhD from UNLV. And also, I'm very glad to have these opportunities to talk about time series forecasting, which has been a strain of a very popular field in data science with all of you today. So today, we're going to start with understanding time series forecasting, and we'll talk about some common questions that you probably want to consider first before jumping into building time series models. And today's focus will be mainly focused on different time series models that we normally use to make forecasts. We'll start with 4 baseline models, which we rarely use in productions. They normally serve as the benchmarks to compare the performance with other models that you build. And we'll talk about the ARIMA models. That is probably the most heard and adopted models in the time series analysis. And we'll talk about a very new model developed by Facebook's core data science team. I'll highlight several characteristics of these models that makes it quite popular to be adopted in industry for the past few years. And finally, we'll talk about the long short-term memory, LSTM models, which is the deep learning applications for time series forecasting. To make them more clear, I'll show you an example of applying some models I highlighted today to forecast Seattle's housing price. Okay, so let's first take a look of probably one of the most popular time series forecasting models this year, the predicting growth of COVID-19. So the data is compiled from COVID-19 forecasthub.org, this website, and you can find a variety of forecasting models from 538.com. Here I only have space to include these 4 models from MIT, UCLA, Iowa State, and COVID-19 simulators. If you're interested in learning more details about all the 15 models, you should take a look at this website. The reason I want to show these models is to let you know that time series models can generate a wide range of different forecasting results because they are all built on different assumptions and domain knowledge. And those assumptions can include something like how infectious the virus is, the mortality rate, or the frequency of contacts we should expect between people. So they could also be built using very different mathematical algorithms, seasonalities, or error rates. But the point is that these models are not trying to tell us one precise number. What's more important is the range of possibilities given the historical data we have. Forecasts like this are much more useful because they help us understand the most likely outcomes as well as best and worst possibilities in those confidence intervals. medical personnel can then adjust or reallocate their medical resources to the most needed regions. Okay, so now let's talk about what is time series forecasting. But even before jumping into using time series to make forecast, you need to think first as what you are trying to forecast even predictable, and also whether the forecast can really affect the fact we are trying to forecast. For example, we all know that stock price is unpredictable. It can spike and plummet in a very short period of time. We call this kind of a trend random walks. So a random walk is unpredictable, right? And the best prediction you can make is to use the observations at the previous time step as what will happen in the next time step. And this is normally what we call as a naive model or persistence model. If you happen to find that the naive models provides the best source of reliable predictions of your time series data, then you should probably think twice before approaching with more complicated time series forecast. Okay, so next let's talk about what is time series. According to the book, Time Series Analysis, Forecasting and Control, the authors defines a time series is a sequence of observations taken sequentially in time, and time series analysis in models to find seasonal patterns, trends, noises, and potential exogenous variables. We got a couple of terminology here. We'll come back to them in a little bit, but simply looking at these very simple definitions, you can see an important distinguish between predicting time series and general non-temporal predictions. So in general predictive analysis, we are predicting the future with the assumption that all previous observations are treated pretty much equally. But for the time series predictions, it adds this additional time dimensions, and this creates a temporal order dependency between each prior observations in your historical data. And because of this extra order component, time series forecast is more challenging to handle than the traditional predictive analysis. Okay, now let's look at some questions I think you should consider before you are about to start a time series forecasting project. First, do you have enough data? And what is considered as enough? It really depends on how accurate your forecast has to be and how far off you want to predict in the future. For example, if you want to say predict a week of revenue for your newly opened restaurants, you probably want to have at least 2 to 3 weeks of historical data, considering there's no major events, which influence seasonality of your revenue. If you only have 1 week of data and predict for 1 week, then your model is pretty much just replicating the patterns of that week. And next, do we have a lot of missing values? And just like building machine learning models, do you need to impute those missing values? How are you going to impute them? Should you use the mean, medians, or the same value from the previous 10 steps, or weighted average? Then do you find any outliers or irregular spikes or drops in your historical data? If so, should you remove them so they won't skew your model's fitting patterns? And next, you want to make short-term, medium-term, or long-term forecast into the future. And this is actually related to what we just discussed, whether you have enough historical data. And another thing to notice that whether you notice any seasonality from your prior observations. For example, if there's always a busy season for your restaurants in July because there's a convention or music festivals in town, and slow seasons in December because your restaurant is located in a city with the majority of migrant populations, then you definitely want to include the seasonal patterns in your prior observations. And then whether you should fit an additional models or multiplicative one, an additive models or multiplicative ones. And to answer this, you should first observe that your time series for the variations across the time frame. If the variations are constant throughout the time series, then additive models should be preferred methods. If you find that the seasonal variations are changing proportional to the level of the time series, then multiplicative methods is probably more appropriate. And the last one is actually a very important one, especially when you are conducting ARIMA or LSTM, the deep learning models. You need to know whether your time series is stationary. So what does that mean to have a stationary data series? To put it simply, a stationary series, their properties like means or standard deviations, they don't depend on the time at which the series is observed. So the series shouldn't have a trend or seasonality. If there's a structure in the data that is dependent on time, then it's non-stationary. And the reasons to have a stationary data is that they are easier to model. We'll come back to this later when we talk about ARIMA. And normally, the common way to stationize observations is to simply remove the trend from your time series. And the standard way to remove a trend is to difference the data by subtracting the observation from the previous 10 steps from the current observations. Okay, so based on what we just described, can you tell which one is a stationary time series from the plots here? Hopefully you can spot the middle one is the stationary series. The left one has a clear increasing trend and very regular seasonal fluctuations. So you can also find the variation increase with the passage of time. So definitely its properties are time dependent and it's not stationary. And as for the one on the right, it has very clear seasonality patterns, right? So you can find the spikes on the fourth quarter of each year, and that is in the beginning of the like a second quarter. So this series is also not stationary. Okay, so now you are ready to conduct your forecast on time series. Basically, the steps to conduct time series forecasting can be generalized into 3 steps. You start with selecting models and instantiate all the parameters in the models. Then you split your historical data into training and test sets. This step is basically the same as what you do to build the machine learning models. And you can even split to an additional validation set if you do have enough historical data. Then you use your training data to fit the models you select and evaluate the performance on the test set. We'll come back to this with regards to several metrics you can use to evaluate your model performance in the end. And if everything looks good, you can throw in the period you'd like to predict in the future into your models. And today's focus will be providing intro on several popular models you can use on your forecasting. They can be generally put into the 3 main categories. The first category is the baseline models. One thing to note is that you normally want to test multiple models in your forecasting project. And it's important to have some baseline models to starting point, so you can have benchmark performance to compare with your more dedicated models. Then there are linear models and nonlinear models. And for time series models, you will have at least 4 elements. Levels and arrows are basically present in all the time series. Level, basically is the baseline values for the series if it was a linear line, and arrows, sometimes called noises, are the variabilities in the data. And the other 2 components are optionals. They can be absent in your time series. Trend is basically straightforward. It is the increasing or decreasing tendency of a series over a period of time. And seasonality is the repeating cycles you can see from the series. Okay, so before we officially talk about the models, let me briefly talk about the example data that I want to show you. This is the median housing price in Seattle since February 1991 to July 2020 this year. The data was reported on a monthly basis. By simply plotting the data, although you can see that some ups and downs, but the general trend of Seattle housing price has increased a lot in the past 30 years. I also decomposed the data so you can see the trend, seasonality, and errors. So clearly from what we just talked about earlier, the data is not stationary, right? And if you want to be more certain, you can always run the augmented Dickey-Fuller test or ADF test and KPSS test. These are two tests to verify if your data is stationary or not. If ADF is insignificant and KPSS is significant, then your data basically is not stationary. Okay, so let's start to look into some baseline models. First, the simplest models among all the time series models is the Naïve models. This model is adopted widely in financial data, and it is simply set for forecast to the last observations in the time series. And it can also allow a simple tweak to add seasonalities into the models. So in that case, you just set the forecast to the last observed values from the same season of the year. So if it's a monthly data, then you set your future value equal to the last observed monthly values, and same for the quarter data. Okay, so the next model is also a very simple baseline models, moving average smoothing. This model takes a moving average to estimate the current values of the mean and further use that as the forecast for future values. Moving average smoothing is simple to compute, and you can adjust the smoothness by changing different orders of a moving average. But the model is pretty much constrained to the same window size and can't reflect the peak or valleys from your series of data. So it's also not robust to outliers or any extreme values. It's pretty much just like calculating the means for a string of the data. The next model, this one is the exponential smoothing model. So these models can handle some of the constraints that are from simple moving average. It basically reduces the lag effects from moving average smoothing and also weighs more on the more recent data than the older data in the series. So the smallest weights are assigned to the oldest values in the series, and this weight is alpha, as shown in the formula, and it's between 0 and 1 as the smoothing factor. So if this alpha value is equal to 1, then basically it's the same as the Naïve models because this model is more realistic. It is normally a go-to baseline models to consider if there's no obvious trends or seasonal patterns in the series. And lastly, let's talk about the extension of the exponential smoothing model, host methods and host winters. So the difference between these two is that host methods allow exponential smoothing to consider another smoothing factor, which is trend. So it's also called double exponential smoothing. And in host winter methods, it further takes into account of seasonal smoothing factor. So it's also called triple exponential smoothing. And because of the seasonal factor, you can also add either additive or multiplicative components as we covered in the beginning. Okay, so now after all the baseline models, let's talk about one of the most popular time series model, which is autoregressive integrated moving average, or ARIMA. And from its name, you can probably tell that ARIMA describes autocorrelations in the data. Autocorrelations, to put it simply, is regressions of the variables against its past values in the series. Here, I want to also mention that you can use autocorrelations plots to plot values by lags in time and identify the autocorrelations. So any values beyond these cone-shaped light blue intervals in the plot, they are considered significant, which suggests that we do have autocorrelations in our time series. And the next component is integrated. It is just how many times that we need to difference data to reach a stationary state. And one thing to note is that ARIMA requires stationary time series as inputs. So we talked about the stationary series earlier. If your time series is not stationary, then you just have to difference your data to fit ARIMA models. And the final one is moving average. It models the next value in the series as the linear functions of the residual errors from the previous 10 steps. So now you probably wonder that how can I find those numbers to fit my ARIMA model? Should I test them one by one? And the answer is no. So you can normally use R and Python's packages to find those optimal numbers for you. They ran grid searches on all the combinations and find the parameters with the least AIC. So you actually don't really need to worry about those manual calculations. Okay, so let's take a look at the model performed on our housing data. Here I use seasonal ARIMA or SARIMA to build a model. It's the same with ARIMA, but with the seasonality component. Since we do see seasonal patterns in our data, I also use the data before 2020 to train a model and use this year's data to test its performance. I'll come back to this in the end when we talk about model evaluations, but the blue line in the plot is the real price and the orange line is the forecast price. So the light orange area is the confidence intervals from our forecast. So you can see that the SARIMA forecast is actually pretty decent considering the data range is between 650K to 780K. The next model I want to introduce called Profit. This model actually gained lots of attention in the past few years. It was developed by Facebook's core data science team. The model is built with a simple structure with seasonality trend, error terms, like what we saw before for normal time series models, but it comes with an extra component, which is the holiday effect. So you can specify special events or national holidays and export their specific effects accordingly. And the reason that Profit has gained a lot of attention in the industry is not just it performs pretty well with data with seasonality and trend, but it also requires minimum data preprocessing. It is pretty robust with a reasonable number of missing values or outliers, which in other time series models can heavily skew the forecasting capabilities. And other than that, Profit also provides the flexibility to change the growth as either additive or multiplicative fit. So you can even specify the maximum and minimum forecast values in logistic growth models, or just run the generalized regressions using the default additive linear models. And another benefit of Profit is that it also gives you abilities to define change points. This is particularly useful whenever there are historical trend changes due to some major events, such as the product launch, etc. Then you can manually define the change points for the models, so the model won't overfit. And finally, that you can customize the seasonal components to whichever granularities that you prefer to see. So it's actually a really convenient models. So here you can see that the visualization generated by the Profit applying on our housing data. The left one is an interactive forecasting model plot built in Plotly. And you can specify the granularities to the preferred time frames. And on the right are the plots decomposed from general trends and seasonalities. One thing to note is that the model also provides forecast uncertainty shown as the light blue band. So you can find that the upper and lower confidence intervals over predictions, which in real business cases is probably more useful than providing the forecast numbers in demand planning. The model also provides decent predictions, but not as good as what we saw earlier from ARIMA models. Okay, and finally, the last model I want to discuss belongs to the area of deep learning. This model called long short-term memory, or LSTM, is a class of recurrent neural networks. It handles sequential data via autoregressive recurrence, and is used pretty widely in speech or handwriting recognitions, or machine translations, and anomaly detections. It is particularly robust to model nonlinear data as long as there are large amount of data. So in the plot on the right, this is a basic architecture of LSTM model. We won't go into details about its structure, but I want to point out that each of the green rectangles is called cell. Within this cell, it compiles those functions and optimization algorithms. So it is basically the memory block responsible for remembering the calculations between layers within it. And it will also pass the memory states as output to the next cell. So that's how the model memorizes from the previous states and learns over a long sequence in time. It doesn't really rely on a predetermined like windows of observations as what we saw in some previous models. So there are two requirements to fit your data as input to this model. One is stationary, same as what we saw previously for other time series models. And the other one is to have scale observations. Because LSTM, they're just like other neural network models. They also expect scale data to fit into the activation functions. And normally the default activation function is hyperbolic tangent. So the output would be between -1 and 1. But however, these LSTM models has the problem of overfitting and tend to carry forward a high degree of volatility in predicting the future values. So it's not the best choice in modeling the data with a strong trend. For example, it's more suitable to predict the time series for rainfall using the LSTM because it's pretty volatile, but not so much to predict the temperature because it normally has a clear trend throughout the seasons. And finally, I apply the LSTM models on the housing data. Specifically, I use two LSTM layers to two dropout layers to avoid the overfitting and rectify linear units as activation functions and atoms as the optimizers, and ran on 100 epochs. You can see that the model actually performed very well. I zoom in on the test data, so you can actually see the forecast and real values are quite close. And it also has the lowest root mean square errors. Okay, and last but not least, let's briefly talk about how to evaluate your time series model's performance. The concept is that the same as you build the machine learning models, you need to basically split the data into training and test sets. And you can even have a validation set on top of that and do a cross validations. And the reason this process is important for time series forecast is because you really don't have access to the future dates data. So you can't get a sense of how your model actually performs. So what you can do is that building the model using a portion of your data as what we can see as the blue square in the plot, and verify the performance on another portions, which is the orange square in the plot. And this test portion should be somewhat at least as large as the maximum forecasting period required for your predictions, which is the red square in the plot. Once you get an acceptable thresholds on your test data series, then you apply your models to do a real forecast in the productions. Here I also list a couple of the metrics normally used to evaluate time series forecast models. The root mean square errors, RMSE, is a popular choice as what I showed in most of the example models earlier, because this model, this matrix punish large errors, And the score is the same unit as the forecast data, so it's easy to compare with the mean values in your time series. However, keep this in mind that nobody can tell you that what is the good RMSE for your model. It really depends on your judgment and domain knowledge to use these metrics to determine the performance of your model. Okay, so here are some references I use in this talk, and that's a high-level overview of the forecasting time series data and techniques. By no means that it's an exhaustive list of models, but hopefully this overview provides you some insights about what time series models you can try before you kick off your next time series forecasting project. And here's my contact information, and thank you for your time.